The third industrial revolution.
Before we look at where we go from here, there's something we need to look at called aggregate efficiency. And it's important because that would enable us to see where we can go in order to improve the economic model, to make it more efficient, and to develop out of this second industrial revolution using the 20th century technologies and into a better system using technologies in the 21st century. Our global economy is slowing down with fossil fuels. If you look at the GDP around the world, a lot of them are slowing down, and that's something that hasn't really improved since the 2008 recession. We haven't got back to a GDP which is anywhere near what it was before the recession. We had, a fairly good global economy prior to 2008, and since then it really hasn't been the same. GDP, by the way, is very simple. It simply means it's all of the goods and services that are being made by that country and what is their combined value in the market. That's all it means. It's the gross domestic product. So the overall national value of what they've made. So we're not producing as much as we were before, so our economy is slowing down, and that is a sign that things aren't as efficient and effective as they were prior. It used to be thought that we just needed better machines and better workers to get more output. But when you actually study economics, you realise that better workers and machines only accounts for about 14% of productivity. Jeremy Rifkin says that the other 86% of our productivity is accounted for through the laws of thermodynamics. Now, when you look at thermodynamics, it's basically the analysis of heat in the universe, heat in our environment. Thermo meaning heat, dynamics meaning movement. When you look at thermodynamics, you see that energy isn't created or destroyed. It can only change form. So it can go from one form of energy to another. So you might burn some fossil fuels, which are energy, and that heat that's created from burning it turns into a gas, which is released into the atmosphere. That's thermodynamics. So the energy has transformed from one particular type into another. It wasn't created in the beginning out of nothing, and it wasn't destroyed. It's always come from something, i.e. dead dinosaurs in this case, and it wasn't destroyed, it changed form into a gas. And this also leads into another element of thermodynamics, which is something called entropy. Entropy is where you move an energy from something that can be used, and then it changes form into something that cannot be used for energy. That's entropy. And our universe has entropy all over. It's where it's where matter moves from a material that is concentrated and hot and together physically to dispersed into the atmosphere and far apart. The particles are far apart and it gets cold. So it goes from concentrated to distributed and from hot to cold. Just like an explosion or a firework, it starts off hot and it explodes out, and as it does so it gets colder and all of the sparks, all the fire burns out and goes cold. That's the universe. It's basically a big explosion. Every stage of conversion, going back to economics, every stage of conversion of a resource, whether a good or a service, uses energy. So for example, to create a good or service, what do you need to do? You need to extract some physical resource, you need to transport it to be processed, and then transported again to be refined, then transported again to be turned into a good or a service, then transported to where it's needed to be sold, and then it gets transported to the person's house in order to be used. And then once it's used and no longer needed, it can be then transported to be recycled or reused or upgraded, or it could be disposed of, basically. But every stage of the conversion, every stage of this process, you have to actually use energy to move it along the conveyor belt of the good or service that's being made. So it needs energy to move it. However, at every stage of the conversion, Jeremy Rifkin says, it results in heat loss. So you're losing heat every time you use energy, and that's thermodynamics, that's entropy. This process is also known as aggregate efficiency. So aggregate means sort of the movement of something in order to get a different result, and efficiency means to make things with less energy required to produce it, or less time, for example. Now, when we look at our aggregate efficiency, i.e. our ability to produce goods and services in a way that uses less time and energy but get the same result, that's aggregate efficiency. We went from 5% aggregate efficiency in 1905 and we got right up to 20% aggregate efficiency by Japan. And that actually was our peak in the current monetary market system. That was our peak. Japan for the whole world by getting to 20% aggregate efficiency using a 20th century fossil fuel infrastructure. So it couldn't get above that because that's just how efficient you can get using fossil fuels and human labour and machines.
The third industrial revolution.